So in my identities video, I found an identity I thought was really cool, which was when you take any normal number, any positive integer, and you raise it to the fifth power, the ones digit doesn't change, or it comes back to where it was. And more formally, if you take a number in positive integer mod 10, raise it to the fifth power, the result is always the same as the original number. Well, that was cool, but I'm wondering, do you have to raise it to the fifth power? Well, quick inspection will tell you you don't have to. 0 squared is 0. So, there you go. And 1 squared is 1. So, you just raise the second power. So, what if we, called those, I don't know, I want to call them first overtones, but maybe they're just second order, right? What about 3? Well, 3, not quite so simple. 3 squared is 9, right? So, how many times does it take 3 to go? Well, 3 goes through the cycle. You get 3, then 9, then 7, then 1, then back to 3. Oh, I skipped 2. What about 2? 2 is similar. 2, 4, 8, 6, and 2. So they take 5. They take all the way up to 5. Then you look at 4. Well, certainly 4 to the 5th gives you a 4, but 4 to the 3rd, 4 squared is 16, so that's 6. But then you multiply that by 4, and you get 6 times 4, which is 24. Still only have to go 3. So it's not the same, right? The rule isn't consistent. It's 0, 1 are 2 are second order, 2 and 3 are maybe fifth order, and then you get to 4 and it's third order. Does it mean something? I'm not really sure. 5? Well, 5, you don't have to do anything. 5 is, again, a second order. 6 times 6 is 36, so again, second order. And then 7? Well, 7 does just what 3 does, I think. Kind of. I mean, it goes to 9, and then to 3, and then to 1, and then to 7. Interesting that 7 and 3 went to 1. 2 never hit 1, but still got back to 2. Well, what about 8 and 9? Well, it's like 8. 8 goes 4, 2, 6, and then 8. So it's a fifth order. It's like similar to 2. The third order, the cube is different, but otherwise they're the same. And 9? 1 and 9. Now that's really interesting, because it just alternates between 1 and 9, 1 and 9. So it made me think a lot of things. I wonder if this works in other bases, right? If you treat the base, because we're doing mod 10 in base 10. So what other bases could we look at? Well, I know what you're likely to say is we should look at base 2. Isn't that where everything starts? Well, yeah. I mean, there's no such thing as base 0 as far as I know. And base 1 is just a tally system. So, and I don't want to even think about, fractional bases, real bases, complex bases. No, thank you. So let's start with base 2. What is base 2? Well, there's only 2 digits. As you raise 0 to any power is 0. You raise 1 to any power is 1. So everything in base 2 is power of 2. Simple. 2, and it matches. Now, base 10 didn't match. It was 5 for base 10, but 2 is 2. All right, let's go a little harder. What about base 3? Base 3 has 3 digits, right? 0, 1, and 2. So 0 squared is 0. 1 squared is 1. But 2 squared is 1. So for 2, you have to go up to 3. Now, if you raise all those to the third power, they're all back to their original digits. So it follows they all have a number. That number is the same as the base, just like 2. But 0 and 1 ought to be squared. I have the feeling that 0 and 1 being squared is going to be a thing for every base. So what about base 4? Well, let's see. We got 0, 1, 2, and 3, right? So 0 squared, 1 squared, same idea. 2. Now 2 squared is 0. And then every multiple after that is 0. So I think we've broken the system. Base 4 does not follow the pattern. It's the first one of these we looked at that's not prime. I wonder if that's something. Of course, 10's not prime, so it may be something else. We'll have to look at this a little more in depth. Well, let's move on. 5 is a prime number, so maybe it'll work better. See, 0 squared is 0, 1 squared is 1. 2 in base 5. 2 times 2 is 4. 2 times 4 is 8, which is 3 base 5. 2 times 3 is 6, which is 1 base 5. And then 2 times 1 is 2, so it goes the way around. So is that 5 times? Let's see, 3, 4, 1, 2. Yes, it is. All right. Then 3 in base 5. 3 times 3 is 9, which is 1 base 5, which is... No, it is minus 1, 4 base 5. And then 4 times 3 is 12, which is 2 base 5. And then 3 times 2 is 6, which is 1, and then you get back to 3. So again, you have to go all the way up to 5. And then finally, 4. 4 times 4 is 16, that's 1, and then 4 again. So that's a cubed again. So that rule, it looks like the rule for the base minus 1 is going to be cubed. What about 6? Does 6 work? It's not prime. 0 squared is 0. 1 squared is 1. 2 squared is 4. 2 times 4 is 8. 8 base 6 is 2. So it only takes cube there. Then 3 cubed is, or 3 squared rather, is 9. Base 6, that's 3. So it just takes squared again. And then 4 squared is 16. 16 base 6, 16 minus 12 is 4. So again, just squared. And then finally 5, 25 is 1 base 6, and then 1 times 5 is 5. So again, the rule of n minus 1 holds for base 6. So 6 works even though 4 didn't. Okay, now it's starting to get complicated. 7. 7 is prime, so I'm expecting it to work somehow. If I raise 0 squared is 0, 1 squared is 1. 3, well, 3 squared is 9. That's a 2 base 7. 2 times 3 is 6, that's 6 base 7. Yes, of course it is. Then 3 times 6 is 18, that's 4 base 7. And then 4 times 3 is 12, that's 5 base 7. 3 times 5 is 15, that's 1 base 7, and then we're back to 3 again. 2 times 2 is 4, 2 times 4 is 8, that's 1, and then you're back to 2, so really only, what is that? Cube 4, that's squared cubed 4th power. So, alright, so it was 2, 2, 4, 7, and then for 4 squared, didn't we just do that? No. Yeah, 4 squared is 16, which is 2 base 7. And 2 times 4 is 8, which is 1, and then back to 4. So that's 4th power again. Then 5 base 7. This is gonna be 7, isn't it? 5 times 5 is 25. 25 is 4 base 7. 4 times 5 is 20. 20 is 6 base 7. 5 times 6 is 30. 30 is 2 base 7. 5 times 2 is 10. That's 3 base 7. 5 times 3 is 15. There's your 1. And then 1 times 5 is 5. Yeah, it's the whole web through. Then 6, I'm guessing it's going to be cubed, right? 6 times 6, 36, which is 1 base 7. and then 6, so that's cubed. So 7 works a lot like 5. 7, yeah, maximum is 7. Now what I haven't asked is what happens if we take 3 to the 7 base 7, or 4, or no, not 3, 2 or 4, because those are 6. What happens? Well, 6 is going to work because it's just going to alternate between 1 and 6. But if I were to take, say, 3 or 2, 2 times 2 is 4, right? We got up to, it was 3 steps up to get to the back to 3 to 2 rather. So my guess is it'll be 3 more steps to get back to 2 again. Probably the same thing with 4. So let's go through it. 2 squared is 4. 2 times 4 is 8. That's 1. 1 times 2 is 2. Yeah, it's how it's going to be. So for 7, it says that you would raise them all to the 7th power, and they will all go back to where they came from. So just like 5, just like 2, just like 3, not like 4 for some reason. And 6, I would guess, works the same way. I'll leave that as an exercise for later. Okay, let's look at 8. I don't trust that this will work. I have a bad feeling about 8. So 0 and 1 are the same as always. 2. 2 times 4 is 2 times 2 is 4. 2 times 4 is 8. So after 2 steps it vanishes, I guess you'd say. 3, well, 3 times 3 is 9, so it's only going to take cube to get up back to 3. 4 squared is 16, that's 0, base 8, so that's almost all crashes. There's something here to do with the base and the, if the base has a 2 in it, of course 6 didn't have a problem, 10 didn't have a problem. Maybe if the base has 2 2's in it? Interesting, I wonder if that's the problem. 5. 5 squared is 25. That's 1 base 8. So then that's cube again. And then 6 crashes out, I imagine. 36 is 4 base 8, but 4 times 6 is 24, which is 0 base 8. So yeah, it crashes out for 2 steps in the cube. And then at 7 is going to rotate. 7 times 7 is 49. That's 1 base 8. And back to 7. So just like all the n minus 1 cases, it's the same. So I guess the question is, it looks like 4 and 8, which have 2 2's in them. Maybe it's if you have 2 of the same prime factor. Well, 9 maybe will tell us. What does 9 do? 0 squared is 0, 1 squared is 1. 2 squared is 4. 2 times 4 is 8. 2 times 8 is 16, which is 7 base 9. This gets harder to do in my head. 7 times 2 is 14. 14 is 5 base 9. Right? Yes. 14 minus 9 is 5. 2 times 5 is 10, which is 1 base 9, and then you're back to 2. That was square 3, 4, 5, 6, 7, 8, 9. Yeah, that was all the way up, right? 3 squared. 3 squared is 9. That's 0. Okay. So I think the rule is going to be you can have multiple prime numbers, but they have to be different ones. Okay. So then that explains why 10 would work, but 9 is not working. So if I go 4. 4 times 4 is 16, which is 7 base 9. 4 times 7 is 28, which is 1 base 9, and then you're back to 4. So that was second, third, fourth power. Okay. Then 5. 5, why do I think 5 is going to be like 3? Because the way I know the way these bases tend to work, they tend to be mirrors of each other somewhat. So 25 base 9 is 7. And then 7 times 5 is 35. That's 8 base 9. And then 8 times 5 is 40. 40 is 6 base 9. 5 times 4 is 20. 20 is 2 base 9. And then 5 times 2 is 10, which is 1 base 9, and then back to 5. Yep, just as expected. 6 squared is 36, which is divisible by 9, so that's 0 again. 7 times 7 is 49, which is 4 base 9? 3 base 9? 7 times 7 is 49. 45, yeah, that is 4 base 9, okay, and then 28 is 1 base 9. 2 times 4, 4 times 7, and then 1 times 7 is 7. So that's 4 steps again, and then 8 will alternate 1 and 8. So I guess that kind of it's the pattern of don't have a square in your base. So I guess this kind of leaves me with some answers but some questions as well. For example, what happens when you go above 10? I'll leave some pictures of what happens at the end of this video. And also, why? What's with the square? Why is it that 6 and 10 work, but 4, 8, and 9 do not work? And is that going to happen again? Where? Where's the next place is that going to happen? Well, let's see, 12 probably will fail then. I guess we'll see that. And 16, of course, will fail. And 27 would fail if I bothered to go that far. I don't think I will. But this is an interesting concept. You get these, the ones that are prime are fields. They have these great ability to divide, and every time you divide you get another number that's inside the system. Of course you can't divide by 0. So they're interesting in and of themselves. But these ones that are partial, like, you know, not just 10 but 6 and, you know, maybe 14, right? Those are interesting, but why do they work? And what do they work? You can't divide, right? You can't always divide cleanly when they're like that. That's probably a topic for another video. Anyway, I thought this was interesting. I thought you might find it interesting. So there it is for your pleasure.